welcome back to another Forge College Explainer. Since we're diving deep into our advanced Solana concepts track, specifically exploring Cloudbreak's data structure, let's just jump right in. In our last explainer, we covered data partitioning strategies in Cloudbreak, where we learned exactly how to slice up massive amounts of data into neat, manageable partitions. But honestly, that leaves us with a pretty glaring practical problem.
Right? We partition the data perfectly, it looks beautiful on a whiteboard, but where on earth did we actually put it? Like, how does Cloudbreak find and route thousands of client requests to those specific physical partitions in real time? How does the system instantly know which server node holds that exact piece of data you need, especially when the whole network is just constantly shifting around? So here's our roadmap for today. First, finding partitions in Cloudbreak. 2, the postal service analogy. 3, the 3 lookup mechanisms. 4, reads versus writes. 5, handling partition hotspots. And 6, takeaways and next steps.
Okay, Section 1, finding partitions in Cloudbreak, bridging static design and dynamic traffic. Let's get into it.
So partition lookup is basically the bridge here. It takes a logical key request, say a specific user's account ID, and translates it directly into a physical partition identifier and a concrete storage endpoint on a server. You can think of it as this incredibly fast, real-time matchmaking service between what your application is screaming for and where that data is actually hiding out on the physical hardware.
Moving on to Section 2, the postal service analogy, delivering the data. To make this super intuitive, just think of Cloudbreak as a massive, bustling city postal service. In this model, the entire network is the city itself. Those partitions we created last time, they're the distinct neighborhoods. The metadata service, which keeps track of absolutely everything, is the central postal registry downtown. And the local caches on your devices, those are your own personal mailboxes. This mental model makes predicting the system's behavior a total breeze. If a neighborhood's boundaries are stable, boom, the mail gets delivered instantly. But if a boundary gets redrawn, well, that central registry better update the local mailboxes fast, or else all your mail is ending up in completely the wrong place.
Section 3, 3 lookup mechanisms, how the mail gets sorted. Now, Cloudbreak actually offers 3 distinct postal primitives to route our data, and it's all about perfectly balancing speed with accuracy. First up is direct mapping. This is literally like knowing the exact zip code for instant delivery. You run a quick, local math calculation and bam, you have the address. Super low latency, but high risk if the city boundaries suddenly change. Then we have metadata-driven lookup. This takes a quick second to actually check the central postal registry. So medium latency, but it's way safer for dynamic, changing neighborhoods. And finally, coordinator assisted. This is literally picking up the phone and calling the Postmaster General because a whole neighborhood is actively being bulldozed and rebuilt. It has the highest latency because of the extra round trip, but zero risk of staleness. It's your ultimate source of truth when things are in transition. To speed all of this up, Cloudbreak uses this beautifully engineered 3-tier caching path. It's kind of like keeping a local copy of the city map. First, you check your client cache, then an edge cache, and finally, the authoritative metadata service. But here's the catch. Faster caching always introduces a slight risk of stale data. You know, your local mailbox might have yesterday's map. To manage that chaos, Cloudbreak relies on version numbers and short time to live settings, basically telling your cache exactly when it's time to throw out the old addresses.
All right, Section 4, reads versus writes, diverging paths for different needs.
This brilliantly illustrates the ultimate trade-off in distributed systems. On the read side of the equation, if you have a hot object getting hammered with thousands of requests a second, reads will happily use a slightly stale local mailbox just to save time. They prioritize speed, write. They can totally tolerate eventual consistency. But consider the flip side, writes. Writes absolutely demand the authoritative registry. When you're fundamentally changing data, you cannot afford to send it to the wrong neighborhood. So writers will often just bypass the edge caches entirely to make absolutely sure they don't lose the mail. It's speed for reads and strict, absolute correctness for writes.
Which brings us to Section 5, handling partition hotspots, when one block gets way too popular.
You are inevitably going to encounter this exact scenario in the wild, the dreaded partition hotspot. Basically, one city block is suddenly getting all the mail, completely overwhelming the local letter carrier. When a hotspot hits, the post office has to act super fast. Step 1, the system detects the hotspot. Step 2, it panics slightly, but, in a highly engineered way, and triggers a split, turning that one crowded block into 2 brand new neighborhoods.
Step 3, it tears down the old mailboxes by sending out cache invalidations so absolutely nobody uses the old address. And finally, step 4, during this whole transition, it uses the coordinator to safely route all incoming traffic directly to the new child partitions.
Now, if you're an operator watching the health of the system, you really need to know what a hotspot actually looks like on your dashboard. You're looking for high metadata churn, rising lookup rates, and a sudden, sharp spike in that high latency coordinator traffic. Those are your early warning alarms. When you see those signals lighting up, it means the city map is actively being redrawn right in front of your eyes.
Section 6, takeaways and next steps. Tuning for performance. So, to summarize everything we've talked about today, number 1, you always have to balance speed with correctness, using direct mapping for pure speed and coordinator assistance for total accuracy. 2, you absolutely must handle reads differently than writes. Caches are a reader's best friend, but a writer's worst enemy. And 3, you've got to use your operational levers, like time-to-live settings and cache invalidations, to survive those crazy neighborhood hotspots. Understanding this foundation is absolutely critical before we jump into calculating the actual financial cost of these systems in our next explainer. So, I'll leave you with this to think about. How exactly will your specific application's read and write ratios handle the next big hotspot? Are you optimizing for speed, or are you optimizing for correctness? Take a hard look at your traffic today, and when you're ready to continue exploring the true cost of that performance with us, head on over to Forge College to learn more about this and other awesome Web3 topics. Thanks so much for hanging out with me for this Forge College Explainer, and I'll see you in the next one.